Linear feedback shift register? Lately I bumped repeatedly into the concept of LFSR that I find quite interesting because of its links with different fields and also fascinating in itself. It took me some effort to understand. The final help was this really good page, much better than the, at first, cryptic Wikipedia entry. So I wanted to write some small code for a program that worked like a LFSR. To be more precise, that somehow showed how a LFSR works. Here's the cleanest thing I could come up with after some lengthier attempts: Python. I named XOR the output of the XOR function, not very correct. However, this is just meant to show how it circles through its possible states. In fact, you notice the register is represented by a string. Not much logical coherence. This can be easily turned into a nice tour you can watch for hours. At least I could smile. Then it struck me, what use is this in writing software? I heard it can generate random numbers, is it true? How? So, it would be nice if someone could explain how to use such a device in software development, come up with some code to support the point above, or just like mine to show different ways to do it, in any language. Also, as Therese not much didactic stuff around about this piece of logic and digital circuitry, it would be nice if this could be a place for newbies, like me, to get a better understanding of this thing, or better, to understand what it is and how it can be useful when writing software. Should have made it a community wiki? That said, if someone feels like golfing, you're welcome.
Since I was looking for a LFSR implementation in Python, I stumbled upon this topic. I found, however, that the following was a bit more accurate according to my needs. The above LFSR generator is based on GF2K modulus calculus, GF equals Galois field. Having just completed an algebra course, I'm going to explain this the mathematical way. Let's start by taking, for example, GF24, which equals 2, A4 by 4 plus A3 by 3 plus A2 by 2 plus A1 by 1 plus A0 by 0, A0, A1, A4 Z2. To clarify, Zn equals 0, 1, n1, and therefore Z2 equals 0, 1, i.e. 1 bit. This means that this is the set of all polynomials of the fourth degree with all factors either being present or not, but having no multiples of these factors. For example, there's no 2xk, x3, x4 plus x3, 1 and x4 plus x3 plus x2 plus x plus 1 are all examples of members of this group. We take this set modulus a polynomial of the fourth degree, i.e., pxgf24, for example px equals x4 plus x1 plus x0. This modulus operation on a group is also denoted as gf24, px. For your reference, px describes the taps within the LFSR. We also take a random polynomial of degree 3 or lower, so that it's not affected by our modulus, otherwise we could just as well perform the modulus operation directly on it, for example a0x equals x0. Now every subsequent ix is calculated by multiplying it with x, ix equals i1x x mod px. Since we are in a limited field, the modulus operation may have an effect, but only when the resulting ix has at least a factor x4, our highest factor in px. Note that, since we are working with numbers in Z2, performing the modulus operation itself is nothing more than determining whether every I becomes a 0 or 1 by adding the two values from px and ix together, i.e., 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 0, or zeroing these two. Every polynomial can be written as a set of bits. For example x4 plus x1 plus x0 10,011. The a0x can be seen as the seed. The times x operation can be seen as a shift left operation. The modulus operation can be seen as a bit masking operation, with the mask being our px. The algorithm depicted above therefore generates an infinite stream of valid 4-bit LFSR patterns. For example, for our defined A0x, x0, and px, x4 plus x1 plus x0, we can define the following first yielded results in GF24. Note that A0 is not yielded until at the end of the first round. Mathematicians generally start counting at 1. Note that your mask must contain a 1 at the 4th position to make sure that your LFSR generates 4-bit results. Also note that a 1 must be present at the 0th position to make sure that your bit stream would not end up with a 0000-bit pattern, or that the final bit would become unused. If all bits are shifted to the left, you would also end up with a 0 at the 0th position after one shift. Not all PXs necessarily are generators for GF2K, i.e., not all masks of K bits generate all 2K11 numbers. For example, x4 plus x3 plus x2 plus x1 plus x0 generates 3 groups of 5 distinct polynomials each, or 3 cycles of period 5, 0001, 0010, 0100, 1000, 1111, 0011, 0110, 1100, 0111, 1110. And 0101, 1010, 1011, 1001, 1101. Note that 0000 can never be generated, and can't generate any other number. Usually, the output of an LFSR is the bit that is shifted out, which is a 1 if the modulus operation is performed, and a 0 when it isn't. LFSRs with a period of 2K11, also called pseudo-noise or PN LFSRs, adhere to Golom's randomness postulates, which says as much as that this output bit is random enough. Sequences of these bits therefore have their use in cryptography, for instance in the A5/1 and A5/2 mobile encryption standards, or the E0 Bluetooth standard. However, they are not as secure as one would like. The Berlekamp-Massey algorithm can be used to reverse engineer the characteristic polynomial, the px, of the LFSR. Strong encryption standards therefore use nonlinear FSRs or similar nonlinear functions. A related topic to this are the S-boxes used in ICE. Note that I have used the int.bit_length operation. This was not implemented until Python 2.7. If you'd only like a finite bit pattern, you could check whether the seed equals the result and then break your loop. You can use my LFSR method in a for loop, for example for XOR, pattern in LFSR 0B001, 0B100011, or you can repeatedly call the .next operation on the result of the method, returning a new XOR result pair every time.
Actually, algorithms based on LFSR are very common. SRC is actually directly based on LFSR. Of course, in computer science classes people talk about polynomials when they're talking about how the input value is supposed to be Z with the accumulated value. In electronics engineering we talk about taps instead. They are the same, just different terminology. SRC32 is a very common one. It's used to detect errors in Ethernet frames. That means that when I posted this answer, my PC used an LFSR-based algorithm to generate a hash of the IP packet so that my router can verify that what it's transmitting isn't corrupted. ZIP and XZIP files are another example. Both use SRC for error detection. ZIP uses SRC32 and XZIP uses both SRC16 and SRC32. CRCS are basically hash functions. And it's good enough to make the internet work. Which means LFSRs are fairly good hash functions. I'm not sure if you know this, but in general good hash functions are considered good random number generators. But the thing with LFSR is that selecting the correct taps, polynomials, is very important to the quality of the hash/random number. Your code is generally toy code since it operates on a string of ones and zeros. In the real world, LFSR work on bits in a byte. Each byte you push through the LFSR changes the accumulated value of the register. That value is effectively a checksum of all the bytes you've pushed through the register. Two common ways of using that value as a random number is to either use a counter and push a sequence of numbers through the register, thereby transforming the linear sequence 1, 2, 3, 4 to some hashed sequence like 15306, 22, 5587, 994, or to feed back the current value into the register to generate a new number in seemingly random sequence. It should be noted that doing this naively using bit fiddling LFSR is quite slow since you have to process bits at a time. So people have come up with ways using pre-calculated tables to do it 8 bits at a time or even 32 bits at a time. This is why you almost never see LFSR code in the wild. In most production code it masquerades as something else. But sometimes a plain bit twiddling LFSR can come in handy. I once wrote a Modbus driver for a PIC micro and that protocol used SARC16. A pre-calculated table requires 256 bytes of memory and my CPU only had 68 bytes, I'm not kidding. So I had to use an LFSR.
There are many applications of LFSRs. One of them is generating noise, for instance the SN76489 invariants, used on the Master System, Game Gear, Mega Drive, Neo Geo Pocket, use a LFSR to generate white/periodic noise. There's a really good description of SN76489's LFSR in this page. Here's one of my Python libraries, Python to implement LFSR. I've tried to make it an efficient that can handle any length of LFSR to generate the binary sequence. You can display all the info at step 2. Output. Also can be visualized like this. Check out the documentation here.
To make it really elegant and Pythonic, try to create a generator, yielding successive values from the LFSR. Also, comparing to a floating point 0.0 is unnecessary and confusing. A LFSR is just one of many ways to create pseudorandom numbers in computers. Pseudorandom, because their numbers aren't really random, you can easily repeat them by starting with the seed, initial value, and proceeding with the same mathematical operations.
If you want to support the channel, please consider subscribing.